Okay, so just a couple quick announcements. So this homework B1 is just as a reminder, if anybody missed it, it's due tonight. There's a 20% per day late penalty, so the availability date is actually until Saturday, but that's to allow for that 20% penalty to kind of unroll fully. So what will happen is you can turn in tonight or really anytime until early tomorrow morning. So there's no need to rush to 11:59. If it's in before 10 a.m. tomorrow morning, you should be fine without a penalty. And then it'll do 20% per day. So then Saturday, if you were to turn it in Saturday, you get an 80% penalty. And then Sunday, the availability window closes because you couldn't turn it in for credit anyway, and the solution sets will go live. So that's how that is there. There's an ICA. And remember, so homeworks don't have a drop policy. They just have this 20% late policy because there's only like 5 homeworks. Canvas activities do have a drop policy. It's like the lowest 7 or something are dropped. So it's pretty aggressive, but the next ICA is due before next lecture on Thursday. And then this week's lab 3, is our first exposure to automating simulation. So in the homework and in lab 2, you did hand simulation where you really were kind of handicapped to not be able to use all of the benefits that we can use with these computer systems. In lab 3, you're going to get exposure to Monte Carlo methods, which provide us an opportunity to study, to use stochastic modeling to study simulation contexts that are static. In other words, they have no state variables. And so we'll learn about that in lab 3. And so that's what's kind of coming up here. Then next week's lab 4, you'll actually be introduced to your first pure simulation platform, and that is NetLogo as an introduction to agent-based modeling. Lab 5 then will be your first introduction to ARENA and discrete event system simulation. So that's the kind of calendar going forward. Any questions about that, about the policies and such? Also just checking online, see if there's any questions here. Pretty clear, hopefully no surprises. Okay. All right, just as a reminder, the Rockwell competition is an option for your final project. The entry forms are due at the end of September, I think September 30th. See the website for details. You don't have to do this, but if you're looking for something different, then this is an option. They'll basically give you some data sets and a problem set, and you'll be unleashed to do it. And you'll have to build an ARENA-based simulation that's sort of based on this. I don't know anything about the context of, for the real world study. So there is but like it's been shipping lanes before, like how do you optimize loading of ships? I'm trying to think what it was before that. But it's usually a relatively complex situation where they usually give you a lot of data. So you don't end up taking a lot of data yourself, but you might have to do the input modeling based on data sets that you can imagine that they've gathered for you. So that's kind of what we've got going on there. If you would rather something more healthcare, then there's a FlexSim, which is a competitor to ARENA competition that I'm also happy for you to try out. And with FlexSim, we can't give you a lot of direct support in the lab because it's not ARENA, but all of the fundamentals of discrete event system simulation are there: entities, resources, etc. There's another one as well, the Simio annual competition, again, very similar to ARENA, so I'm willing to consider all those. So as you're thinking forward, you really don't have to think about forming your project teams until probably after the midterm, like the week after the midterm. So we got time, but the registration for these competitions is usually, like in this case, I think it's September 20th for FlexSim. I don't know what the Simio constraints are. Like I said, September 30th for the ARENA one. So if you are thinking about doing these, you do have to think about entering into them soon. All right. Okay, there we go. So questions, pretty clear. Okay. All right, let's skip ahead. All right, so where we've been so far is basically learning how to generate this table, which is your homework B1 table. So if you understand how to do this table, you should get finish the second problem of homework B1 kind of with flying colors. So, if you guys recall in homework B1, I basically give you this table of durations up here, and I give you an end time, and I ask you to start at time 0 and figure out the way the simulation would run, given that these are the activities that were provided. And that generates a timeline. You don't have to draw a timeline in your homework, but this is a timeline that kind of summarizes the output of that table. And if we look closely at this timeline, at say just all of the arrivals, then we can see all of the inter-arrival durations pop up here. So there was a question last time about, well, if I know all the inter-arrival durations, don't I know all of the arrivals? Can I just schedule them ahead of time? And my answer was that you absolutely could, but that can get you into trouble, as we'll see in a second, for things like service durations. And in general, we usually aren't given a list of durations. We're usually given a parameter or parameters for a random distribution. And so when you draw an arrival duration, you draw just from a random, you don't have all of them, you just have the next one, and you just draw a new random one. And so it wouldn't really make sense to populate all of the arrivals because you don't really know how many arrivals you need. You just draw an arrival when you know you need the next one. And so we see all of those out there, and because we know their durations ahead of time, or we can predict them ahead of time without running a simulation, we call those activities. So that's the term we've been using. And so durations you kind of know before running the sim. Now I can put in departures here, and those departures reflect the service durations. And so those service durations I know ahead of time, but I don't know when the service durations are going to start, because they're sort of coupled to these arrivals here. So even though this service duration ended here, so if I try to highlight that, even though this service duration ended early, I can't start the next service because no one's arrived yet. So I have to wait for an arrival just to start the next service. So this arrival that I had to wait for here, and then I have to wait to start this 8-minute long service. And so that gap there is something that I couldn't have known ahead of time. So we refer to the actual durations of services as activities because we know when you start service without running a sim, we have a model for how long, or at least a random model for how long each one of these service durations should take, but we don't know these delays. And that's why we run the sim, is to figure out these delays right here. And so that delay, we refer to it as a delay because it depends upon the state of the system. In other words, even if I know this service duration, it depends upon whether someone has actually arrived yet and whether someone is currently, even if this arrival happened, if the previous arrival is still using the server, the service duration couldn't have started. And so this delay is something that we only can know from running the sim. And so we get a bunch of these delays throughout here that we know only after running the sim. So we put all those together, and those delays end up being the kind of important output that helps us gauge the performance of our system. These are the slack that's left over when the two things we do know about, the inter-arrival durations and the service durations, don't quite line up in a convenient way. That's where we get delay. All right, so an activity I'm going to call an unconditional weight. Its duration does not depend on the conditions of the system. So we often refer to the completion of an activity. Well, so the completion of an activity is an event that we sometimes call a primary event. So starting an activity also requires scheduling an event. So so there was a question earlier about, can we think of an activity as the length of an event? And I said, we have to be a little more careful about that. Every activity has an event at the beginning, an event at the end. And every time you get to processing one event, then you might have to schedule the next event. So it's really the end event that's more associated with the activity than the beginning of the event. Because when an activity starts, it generates its ending event. So that's why we refer to the ending event as a primary event. And so hopefully you get a feel for that as you've done those hand simulations. You're like, oh, somebody just entered service. I need to schedule when they're going to get out of service. So that puts a new event on the calendar. So that starting of service generated that new event, that primary event. Whereas the delay is a conditional weight. It depends upon the conditions of the system. So like I said before, it reflects kind of a temporal misalignment of activities operating in parallel. And so our job as industrial engineers or operations researchers is to adjust the kind of operational engineering structures to try to minimize these delays. So, if you're thinking about, we do this in our personal lives all the time. You might want to order a coffee, and you might say, well, I could do thing X and then go to the coffee shop and order my coffee and wait. Or I can take the advantage of mobile ordering, do a mobile order while I'm doing thing X, and then my coffee will be made while I'm working on thing X. And then when I show up to the coffee shop, I don't have to wait. So by restructuring how the order process worked, then I could get rid of that wait. And we could simulate the effect of those things in a discrete event system simulation. Okay, so delays don't generate events, but by changing system state, events squash delays. And so you could say, well, how long does this person have to wait in the queue? They have to wait in the queue until some other person's service ends. Well, that other person's service will end when that certain event is hit. So that event might kill the delay. So delays are ended by events, but delays don't generate events. Let's see if that makes sense. So we can manage delays by managing our state variables like internal lists, like the checkout line. So are there questions about this distinction between delays and activities? Talked about this a lot, just kind of gone into more detail about some of the terminology we might use, unconditional weight versus conditional weight, primary event, but it's all the same story I've been telling so far. This makes sense, this event scheduling worldview kind of side effect. Yeah. So the question was, is an activity a weight we can control, whereas a delay is a weight we can't control? That's one way to think about it. I would say an activity is something that we've committed to a model of that does not vary with the state of a system. And so in reality, let's say 2 of you show up to class, and that may affect my pace, whether there's 2 of you in here or 100 of you in here. Like just seeing only 2 faces out there versus 100 faces may affect me. But it may be so little of an effect that when we model the system of the classroom, then when we model my pace, we might just say that my pace comes from a distribution which does not depend on how many people were in the classroom. So an activity reflects a choice by the modeler where they're saying this random distribution, its parameters are known ahead of time and will not depend upon how things unroll in the system. So, so that's kind of, so I wouldn't call it, I have to be careful, I wouldn't call it control, but it's, you have much more knowledge about the activity, whereas the delay you have no knowledge about, and that's the reason you run the simulation. Okay, any other questions? Great question. I'm also gonna glance online here. Okay. All right. All right, so in more real world cases, delays emerge from implementing concurrency with limited shared resources. So ideally in a real world, we would show up to a resource only when it was idle. So a car would never have to wait for pedestrians and pedestrians would never have to wait for a car. That's never gonna happen, but we can try to implement things like smart stoplight timing, for example, that try to get us closer and closer and closer to that ideal where there's no contention for resources. And so this resource contention, where a bunch of different processes compete for the same resources and can't manage to get their timing coordinated, is what generates delays. All right, questions? Pretty clear, okay. Questions online? Good, okay. All right, so so this is just kind of the review what we did last time. Generically, when you grab an event off of the future event list, you're gonna set the clock to the time of the event. You're gonna schedule new events based on the future end, that primary event of any new activities. And every arrival generates an activity of waiting for the next arrival. So whenever you process an arrival, you must schedule a new arrival. And so that's something that's often missed is that you don't think about waiting for an arrival as like an activity, but it is. It's just as much an activity as a service. And so whenever you process one arrival, you start the activity of waiting for the next arrival. So you have to schedule the next arrival. The start of any new service is an activity, and thus must generate a primary event to schedule the end of that service. So this is what keeps the clock going. So in the event scheduling worldview, the only thing that keeps the clock going is you scheduling the next event, and you jump in irregular time steps. This is very different. Like in an agent-based model, typically things step along at a time step, like every microsecond. And you move the world along every microsecond by microsecond, even if nothing has happened. This jumps over all of those microseconds where nothing has happened, only to the next time something actually happens. So that's the view here. And then we hit an end event eventually, and we stop the sim. And so hopefully all that made sense in your homework. I won't belabor this too much, but this is just, I'm going to step through all of this just here. If anyone does have any questions to this is the same stuff we did before. In the homework example with the single channeled queue, or then, we have certain logic that goes along with an arrival event. We have certain logic that goes along with a departure event, and we have very little logic, but that goes along with the end event. And by following that logic, you gradually can populate this table. And that's what we did last time, where we just stepped through this. And there were a lot of great questions last time. Hopefully, by doing the lab, and hopefully, some of you, those of you who have started the homework or turned the homework in, feel pretty confident with this. Before we move on to new things, are there any last lingering questions about this hand simulation stuff? Is there anything that doesn't make sense about this table? Online as well. Does everybody feel comfortable? Okay. Unfortunately, after this homework, you're not going to have to, well, I mean, of course, midterm or something like that, you're going to have to know about a hand simulation. On a midterm, I might show you a table like this, and I might, there might be things missing, and I'll say, what should go here? So you're going to need to know how to do these things. But from this point on and towards into your career, you're not going to have to hand simulate. But you may have to, similar to the midterm case, you can in Arena have it show you its event calendar. And just like when you're trying to debug what might have gone wrong in your hand simulation, you can use Arena's event calendar to help you figure out if maybe something that you thought was programmed one way was not. And so you might have thought you were using minutes everywhere, but you had one process block using seconds. And because of that, you're seeing a bunch of events pile up where they shouldn't be. And that's because the services are completing maybe much more quickly than they're supposed to. And you might be able to diagnose that by reading the future event list. And so being able to read these event lists is an important skill to have when moving on into simulation. But actually having to generate them yourselves is something you won't have to do unless you go into programming these software packages. So yeah, that was my stalling for 30 seconds. So anything come up over here or over here? No. All right, great. Okay, so we're kind of at the end of a chapter here. So the terms that I want to make sure that you feel comfortable with are system and model. State, the notion of system state, because these are dynamical systems, they have system state. And because we're treating them as discrete event systems, then that state changes on events. And one of the important state variables that keeps track of things is the clock, which all of these systems have. We have entities and attributes. And then going along with that, we have lists where we can put those entities inside the simulation. And we have event notices, which fit on a special type of event list, the event list or the event calendar. And then finally, we have the notion of activity and delay. And the activity is what ends up setting up the timing for the event list, and how the activities intermingle is what ends up generating delays at the end of a simulation. So those are the kind of key concepts for this chapter. And so any clarifications needed about these things? Pretty clear. These are the terms that we might use moving forward. Okay. And anything online? Looks good. All right. Okay, so let's do a quick attendance exercise just to keep everybody awake. So do a question 1 for today here. And I'll put the link in the chat as well for those following along at home. And so I guess the question I'll ask for question 1 today is, what is the name we give to the event that is scheduled at the end of an activity? So every activity generates a special event at the end of that activity. You can't start an activity without scheduling this event at the end. What's the fancy name that we give for the event that we schedule at the end of an activity? And again, this is just to keep track of everybody's here and paying attention. If it's, it's not graded for correctness, it just has to kind of make sense as an answer there. So I'll put that in the chat in case it was missed. But the question here is, what is the name? What is the special name we give to the event scheduled at the end of an activity? All right. And then so what's the answer to that? Anybody got a guess? Yeah. Well, so departures generate events, but I'm looking for something more general term. Let me have that general term. Well, the end event is at the very end of the simulation. So this is sort of a funny name. What's the event that happens at every end of every activity? So activity comes, and we need to schedule this that shows the activity is going to end. Primary event, that's what I'm looking for. So the primary event is the event that happens at the end of an activity. So we associate events more with the ends of things than the starts of things. And so service starts, and then you have to think, what happens when service starts? I have to schedule the end of the service. So the primary event happens at the end of the activity. So that's a term we use, primary event. Okay. All right, so I mentioned that this upcoming lab 3, you're going to be introduced to Monte Carlo simulation. That is your kind of first exposure to doing automated simulation on your own. But the Monte Carlo simulation doesn't have state. So it's not a dynamic simulation framework. So the question is then, how do we use tools to generate dynamic outcomes? So like outcomes from discrete event system simulation. And so before we get into ARENA, we could say, well, how could we do this in a spreadsheet? So right now, so far, you've been doing hand simulations in tables, maybe implemented inside a spreadsheet. But of course, we can use spreadsheet logic to end up generating these traces for us. But we have to we have to be careful about how we do it. So we can think about programming languages in a couple of different groups. So and I'm not going to quiz you over these different groups. This is me just giving you context for where spreadsheets come from. So there are procedural programming languages like C, Fortran, Pascal, BASIC, where the focus here is on procedures and subroutines that manipulate data structures. Their programs are lists of computational steps, and we refer to them as being imperative. And that means that the statements change the state of the program. And so the program has state. It's a dynamic entity, and you start at the top of the list, and the state is one thing, and as you go through the list of steps, the state changes. So that's one of the things that's special about procedural programming languages. Now there's sort of a modification of those as they got a little bit more enhanced over time, object-oriented, like C++, Objective-C, Java, to some extent Python. So in these cases, we've got languages where the data structures carry with them so-called methods to manipulate them. So objects interact with each other by way of their methods. So you have a person object interacts with a room object, and the room object may have a method for turning the lights on and off. So you can think about the data being hidden, encapsulated within the objects and not accessed directly, but still we have the notion of state, and that the room has a state. The lights are on, the lights are off, and the methods are interacting with it. So it's still there's a list of steps and you respond to the state of the objects in your logic. Now, there's another group called functional languages. Now, functional languages like Lisp, Scheme, Haskell, ML, and as I'll say in a second, the common spreadsheet, these are very different. Here, a program output is a mathematical function of its input. It is not a list of steps. And so these are declarative. Programming is done by employing expressions of relationship. It's much more kind of mathematical. There are no side effects that change the program's state. There's like an ordinary differential equation, for example, is similar to this. You say x dot is equal to negative x. That is saying that over the entire execution of the system, that will always be true. dx dt will always be equal to negative x. No matter if it's at time 0, at time 5, at time 1 million, that will always be true. It's an expression of relationship. The relationship between the derivative of x and x itself is dx dt is equal to negative x. There are programming languages that operate the same sort of way, and we refer to them as being declarative. And these declarative that don't have a program state, well, one of those is the spreadsheet. So spreadsheets are a declarative programming languages. They capture relationships between cells. They're sometimes called cell-oriented data flow programming. They don't specify steps. They just specify relationships. You just say, this cell is always twice this other cell. This other cell is always the square root of this other cell. And those relationships always hold. You go in and you change the inputs, you can type in something in a cell, and it creates sort of these domino effect all over the spreadsheet, right? And so that is an outcome of your changing input, but you didn't see how it happened. You didn't know which cell changed first. You didn't know how the program did it. So there's no list of steps. So no of how do I update this cell based on this cell? And then how do I update this cell based on this cell? And in what order should I do those things? None of that's all abstracted away from you. And that was what makes them a declarative language. Now, because of that, they have no state, then it's hard to see how could we possibly run a discrete event system simulation in a spreadsheet, because a discrete event system simulation requires us to maintain state variables and update those state variables at every event. But we have no state in a spreadsheet. So this is really sort of instructions for how to do the bonus of homework B1, where in B1, I said, as a bonus, can you implement the same thing you did in question 2, but do it in a spreadsheet where the spreadsheet does all the math for you. And if you wanted to generate more rows, you could just fill down and it would do it for you. There's no hand simulation involved. So how do we do that? So this in some ways is a recipe for how to do the bonus for this homework. And so the idea here is if you think about the homework bonus, this is basically where we would start. So if you go to table 211, which is where I kind of told you could start, but you populate these things with the information I gave you from question 2, then you'd have lines of every row is a customer, and every customer has an associated inter-arrival time. So there's always going to be a 0 for customer 1 here. That could actually be empty if you're matching kind of my notation from the homework assignment. And then every customer has an associated service time. So we want to say is, can we, without the notion of state, simulate this dynamical system so that the spreadsheet will automatically fill in everything else for us without us having to manually do anything? So what dx dt, what ordinary differential equation, what relationships do we need to specify to get that to happen? So, so that's what we're kind of going to walk through here. So if we think about it, the arrival time one is one of the easiest ones to do. You guys have already asked questions about it. You said, you know what, I know all the inter-arrival times. So it's easy for me to figure out all the arrival times ahead of time. I just add up all these things together. So if I think of that in terms of a spreadsheet, I think about what relationship always holds. What's the dx dt equal negative x that always holds? And for the arrival time, the relationship that will always hold is that the current arrival time is the previous arrival time plus the current inter-arrival time. So I didn't write this in sort of Excel syntax, but you could imagine in Excel or Google Sheets or whatever, that you could start for the formula for any arrival time, like if I can manage to get this one backwards. So if I can manage to get this over here, maybe I'll just do this. So this 14 down here, that 14, I could imagine a formula where I would say, equals the cell right above it, whatever that ends up being, C3 or something like that, plus the cell next to it. And so that formula where it's just this cell plus that cell, that would go here. And if you filled that all the way down, then you get all of the arrival times. So that's pretty easy. And it kind of makes sense because it sort of just means that this column is the cumulative sum of this column. So that's kind of one sort of easy formula. So how do we get some of the harder formulas here? And I see some comments here in the chat. Let me make sure. There was a comment from a couple of minutes ago. It's basically just a bunch of ifs statements, correct? I'm not sure which that's referring to. The spreadsheet case, behind the scenes, we don't really care about how it's implemented, but if you want to think about maybe an imperative language, yeah, you can maybe think of it as a bunch of kind of if statements where you're constantly referring to states. So that if that question was about the imperative programming languages, then yes, a bunch of if statements is pretty much what an imperative programming language is, whereas the declarative language, again, we don't have state, so there's no if, there's no predicate. So, and then there was a comment here, I think it's more comprised of formulas that reference previous rows. So that's the comment about this spreadsheet. It's the formulas relating to the rows, not about state. All right, so let's think, well, how do we do time service begins? Well, I need to think about a relationship that is always true that refers to time service begins and the other variables that are in my system. Well, if I think about it, the time service begins is always either going to be, well, it's always a maximum of two things. It's either the current arrival time, because that would mean that a customer arrived and they immediately went into service. Or it might be that that customer arrived and it was busy, so they couldn't get into the server. So in that case, I have to look at the previous customer's service ending time. So it's the maximum of one of those two things. It's either immediately when the customer arrives or the previous customer's end time, which will end up being later than this arrival time. And so that will be when this service begins. And that's how I would end up populating this thing. So if I look down through here, I can always see that the service begin time is either matching the arrival time, or if I scroll down through here, like 18 is later than the arrival time. And the reason 18 is later than the arrival time is it will end up being the time the previous customer was ended their service. Now I populated this column early but this column depends upon this other column. So if you were to fill this down without filling everything else out, you would get nonsense here. But I'm just kind of like, there are real formulas here, I've just hidden them away. So right now we don't have enough information to actually populate all these formulas, but that will come once everything snaps into place. That's the other weird thing about declarative programming languages is that there's no like intermediate step that you can check. Everything just has to be right, and then it all snaps into place, and then you get your output, which is based on these inputs, where the inputs are the interarrival times and service times. All right, so this is our first kind of more complex formula here. Are there questions about this formula? Does this make sense as what you would implement? So this would be like in Excel or in Google Sheets, it would be like equals max, and then you'd end up saying the current arrival time or the previous service ending time. So you'd end up the cell formula for this, the cell formula for this, and the max of the two of those. So does that make sense so far? All right. See if there's any questions online. Also check the meeting pulse. Okay. All right, so next thing is waiting time in queue. Well, if we know when their service begins and we know when they arrived, it's easy for us to calculate how long they've waited. And that's just a subtraction. Whenever their service began, subtract off their arrival time, and that's going to tell you how long they waited in the queue. And so that's an easy one there. And so we can see that most of these customers didn't have any waiting time. So we should see that their service began at their arrival time. A couple of them, like this 1816 one, had to wait for a certain amount of time. So that's pretty much done there. And then, all right, so when does their service end? Well, again, thinking in terms of relationships, we have to not worry about how things are calculated and just think about the relationship here. And the relationship here is if you know when the service begins and you know how long the service takes, you know when the service ends. We don't care about how the heck we know when their service begins. But the theory is if I knew when the service begins, I add their service time, I can figure out when it ends. So I can generate an easy formula here where I just look at service begin, I add service time, I get service end. And then from that, then I can run these stats. Now, really, everything from this point over, that was the simulation. That took care of everything for us. Once I populated the time service ends, it then figured out the time service begins. So the time service begins depends upon a previous time service ends. And the next time service ends depends upon a current time service begins. And so that is what ends up making these two work together and allows it to populate this for all of the customers. So all of my information that I normally would need to get by running through step by step from time to time to time, event to event to event, instead of spreading it out over time, I spread it out over space of the customers, and this is effectively my whole simulation. And now I can run cumulative statistics on my whole simulation, and I can say, well, how long did each customer spend in the system? And so I can do this kind of analysis here where I'd say, well, let's see when they ended, when they got there. That says this customer spent 5 in there, so that's the response time for this particular customer. And then how long is the server, was the server idle? And so I can look at, this is a little more complicated one here, but the key feature here is I look at the time the service begins minus the previous time service ends. And if there's any gap between these that's positive, then that's idle time. If the gap between these things is negative, then it's 0. That means that there was no idle time there. They just went immediately into the next service after the previous service. And then I get this whole table. And so that's how we generate this here that has the same information as what you've done by hand up here. And you can now spot check these things. So if you do the bonus in homework B1, you can then double check your work on question 2. And you could do that by, picturing, how do I calculate some of these things? Well, so I could go forward and I'd say, well, let's see. I know that I calculated that customer 3 departed at time 13. So let's look down here. Customer 3, when did their service end? Time 13. So it matches. So these two things, fit. I could say, all right, well then, I think they spent 7 in the system in the Excel version. Well, how long did I see they spend in the system up here? Well, I see that when they departed, the cumulative response time jumped up by 7. So, yep, it's 7 there. So the same information is being mimicked in these two different forms here. This one you did by hand, going from time to time to time. This one you did automatically, going from customer to customer to customer. Where again, things here spread out in time here, they're spread out in space here. And then I could do other comparisons as well. Like this customer, time customer spends in system. Well, if I were to add up all these things, then I'd end up getting this 16 here. So I know that when by the end event at time 15, then I know that I've had all of the departures so far have added up to this 16, which is this 1 + 8 + 7. So it all ends up matching. So this is exactly the same information as this, but just calculated in a fundamentally different way. All right, so are any questions about this? Do you see the congruence between these? This is your bonus. This is your question 2 that you've got to do, that you're required to do. This was totally automated. Once you put the formulas in, you could just fill it down and it would keep going. This one you had to do tediously by hand, where every row is another little bit of torture. Any questions online about this? For the bonus question, we were limited to 5 customers. And so there's a question online for the bonus question, the homework, we're limited to 5 customers. you do, I think I don't recall how many I gave you, but if I gave you 5 customers, then yeah, that's where you've got to stop it. So you couldn't fill it down to infinity unless I gave you more interrival times and more service times. So so you do it as far as you can, and then once you kind of run out of those interrival times and service times, then don't do another customer. Any other questions? Okay. All right. Okay, so a couple of things here to note. Regardless of which way you do this, the outputs are highly variable. And in general, they'll be random. In general, when you do this, if you were to generate an Excel-based spreadsheet to do a discrete event system simulation, then you wouldn't hard code these interrival times or service times. You would actually go into Excel, and we'll see how to do this when we get into actually drawing random numbers. And you would say, draw this from an exponential random variable with a mean of 6. And then every row would be a new draw that Excel would do for you. Likewise, service time, you'd say, draw this from a normal random variable with a mean of 10 and a standard deviation of 2. And it would then draw these for you. So every time you reopened the Excel, you'd actually get different numbers. And so normally these things would be totally random. Even when I give you the numbers, you don't know where they come from. You can see a lot of variability in the outputs here. And so in general, how do we make sense of variability? And that'll be the back half of the class after the midterm, and where we're going to have to dial in statistics. In other words, this spreadsheet or that hand simulation is an empirical system, just like any other empirical system. When scientists work on mice, there's going to be variability from mouse to mouse to mouse, which is why they have to use stats, which is why we have to use t-tests and ANOVAs and so on in this class, because our sims are going to generate the same sort of variability that you would get in any empirical system. And so even though we're doing computer simulations, which you might think computers deterministic, you might think programs deterministic, we're generating the variability, which makes them just as difficult to deal with as a real system out there in the real world, a real factory, for example, where every time you run that factory or every day you go to that factory, you get slightly different numbers. And how do we deal with that? And so that's something that I'm going to touch on here in just a second when I'm going to do a little post lab 2. But before we do that, any questions about any of this? That's kind of my last slide on the stuff you might use in homework B1. Okay, any questions online? All right. All right, so to wrap up then let me hop over into a slightly different, since we've all done lab 2 now, let me reshare. All right, so Muffin Sim, this lab here, which was partly an introduction to our hand simulations, but also partly an introduction to batching, and which is something that will come up later in the class as well. So I'm just bringing up the chat here again. Okay. All right, so Muffin Sim, these muffin batches. So what do we do in this lab? So we modeled this process here, which really could be viewed as an inventory management process, as these muffins that come in, and once you have enough muffins available, then they can be put into an oven together, and you have to wait for the oven, and then they come out of the oven finished. So the question is, how many muffins do you wait for before you put them in the oven and then send them on their way? And there are a couple of different ways we could have modeled this. So you can model individual muffins as entities. The advantage there is it's easy to handle limited oven capacity because each muffin, if the oven's got 30 capacity and you have 28 muffins and 6 arrive, then it's easy to sort of tell that, okay, well, I need to take 2, put them in the oven, and the other 4 have to wait. So there's a lot of high resolution in doing it that way. The downside of that is you had 6 muffins arrive simultaneously. So there's a lot of simultaneous arrival events and simultaneous departure events, and that can be sometimes tedious to deal with in terms of the logic. So another thing you can do is actually have muffins arrive as batches. And so in that case, we have only one arrival per arrival event, and only one departure per departure event, because the whole batch is arriving and departing, but you have to deal with generating these partial batches. And so this is the angle we took in the lab 2, where you had muffins arriving as a batch. And so each line was a different batch number, B1, B2, B3. And then occasionally you had to break those batches apart and send partial batches through and leave the other partial batches waiting for their turn next time. So that is one approach we can do to this sort of setup here. And it is possible to do both of these things. So in Arena, we'll see that we can actually have muffins arrive individually, but then later bundle them together in batches and then unbundle those batches so you have individual muffins again. So there are ways to combine these two, but we were experimenting with partial batching here in lab 2. So any questions about that setup of lab 2? Did everybody sort of feel like they understood what was going on there in the question for lab 2 and the main problem for lab 2 before we get into the analysis of the outputs here? Okay. All right, so are there other sorts of systems that look like our muffin sim? So in other words, other systems where you've got deterministic arrivals, where you've got every day, you know you're going to get an arrival. You just don't know something about the arrival. Like you don't know how many muffins arrive every minute. You know there will be muffins that arrive every minute, but you just don't know how many. Well, one example of that is the stock market. And so people, when they build discrete event system models of the stock market for like portfolio management, they have to deal with this too. They'd say, well, at the end of the day, did the price go up or down? And how much did it go up or down? We know the price is going to move from day to day to day. We just don't know how much it's going to move. And so they use random variables to represent how much the price changes from day to day to day. And they might make assumptions, kind of like we did in the spreadsheet here, where the expected value of tomorrow's price is equal to today's price. And so the little increments may have a mean value of 0, and that creates what's called a martingale. And so a martingale is a random process where the expected value of the random variable in the next step is exactly the value that was drawn of that random variable in this step. And so so this is, although it seems very different than muffins, it's simulated in very much the same sort of way. Every day you get a random number, which is how much the price changes or how many more muffins you have. And so that's where the randomness comes into play. It's not how much time is in between arrivals, it's how much happens at each arrival that we know is definitely going to happen. So that's another thing that we were trying to model in this muffin laboratory here. All right, so any questions about that before we get into stuff that I'm most excited about, that I'm hoping you will be moderately excited about? All right, so what did we do? So I had to do this annoying thing with your ASU ID. And so there were 10 different muffin schedules. So those are like 10 different random number draws. And so if you had your ASU ID ended in 0, you got a certain set of muffins. If it ended in 1, you got another set of muffins. So here's the one I think that I don't remember for sure, but I think this is the one that where the ASU ID ended in 0. And so in here, we saw that if you simulate this whole thing out, then the greedy policy gives you an average time in system per muffin of something around 3.93 or something like that. But the nearly full policy gives you something around 4.15. So just for that policy, so just for that, ASU ID ending in 0, then you might say that it looks like the greedy policy is making the average time in system lower. So the greedy policy is maybe better than the nearly full policy. Now that's just on that one simulation. Now, there were 10 different models that I gave you. So there were each one, so one of you could have had a 10% chance of getting this or one of the other ones. And so So yeah, so the question here is, were you just, if you got this one, if this was your example, is this meaningful? Is it statistically meaningful, and is it practically meaningful? And so can we trust that this just wasn't good luck or bad luck, that this greedy was so much better performing than this? And also, even if we can trust that this is generalizable across muffin schedules, does this effect size here, is it actually operationally meaningful? So it might be that the greedy policy is better, but it might not be that much better to justify changes in the operation that maybe they need to completely change how their whole assembly line is set up to implement the greedy policy. So so to sort of experiment with that, these are what we had you do is have, if all of you got together and pooled your results, then you'd actually get these data. So here we've got, like, this is ASU IDs ending in 0, ASU IDs ending in 1, ending in 2, 3, 4, 5, 6, 7, whatever. So I've got all 10 of the greedy policies here, and I've got all 10 of the nearly full policies here. So we've actually put in parallel, you've turned them into like parallel simulators. So inside Arena, I can tell Arena to say, there are 10 cores on that machine. I want you to run a simulation on each core of that machine in parallel, but use different random number generator setups for each core. And it will run 10 different replications of the same experiment, just different inputs with different outputs, but the same system. And that's what we did here, is that we, in parallel, you guys turned into the 10 cores on that computer over there, where each one of you was running a slightly different random number stream, but you were using the exact same system. And you got these outputs here. And so if I look at the circled one, that's, I think that was the same replication as I had on this previous screen. I'll go back. Yeah, I think it is the same one, but the axes changed. Then I see here that this effect that I happen to see in that pairing seems to be kind of generalizable. The blue lines tend to be higher than the red lines. But if I was just had bad luck and it happened to be that I picked a schedule where this was the greedy one up here, so if the greedy policy was actually this upper one here at like 4.1, if it happened to be for that same muffin schedule, the nearly full was down here at 4, then that would actually give me a very different result. So it really shows how it's important for me to run this experiment multiple times. So in a stochastic simulation, I cannot ever just run it once and then draw a conclusion. So that's kind of one thing I want you to take from that, is that just because in your particular schedule that you got, the greedy was better than nearly full, we don't know that that's true across all schedules. It might have just been a good day or a bad day for muffins that day. So we can think about this. Well, now that we have 10 replications of this and 10 replications of this, do we know of a statistical test that can rigorously tell us that the greedy is on average quicker than nearly full? Does anybody have a guess for that? What is a statistical test which helps us infer that the mean of one population is lower than the mean of another population? A t-test, that's right. So you could use a t-test on these data, and if that t-test came out with significance less than 0.05, then that would reject the null that these two policies are equivalent. And you could then say these policies, to statistical certainty, I'm going to say with this variation, there's a 5% chance I'm wrong, but I am going to claim that based on these data, that greedy is faster than nearly full. And that's what we would use a t-test for. Now, there are some issues with using a t-test for this. If, for one, we ran the same policy on the greedy as the nearly full. A t-test, a pure t-test, requires you to have, every time you run a replication here, you would have to use a totally different muffin schedule for another replication over here. So these 10 muffin schedules would have to be different than these 10 muffin schedules in order for me to run a t-test. That wasn't the case in your guys' case because they were paired. You had a muffin schedule here that you then use for the one over here. So we had the same muffin schedule being evaluated in 2 different policies simultaneously. So we're technically not allowed to use a t-test for this. We have to use a special type of t-test that's like a specialization, and that's a paired t-test. So we actually are going to need to pair these things together. We're going to need to tell the t-test that this red one and this blue one use the same, they were paired together. This red one and this blue one, they were paired together. And then we have to do the test on that. So that's the reason why we have to recognize in our experiments when we've accidentally or on purpose paired outputs together, or else we won't actually be able to make conclusions. Now, what I implemented with you in lab 2 is something we're going to learn about at the end of the class, at the end of the semester, and something we call common random numbers, where we give the same random numbers to 2 different simulators to better understand the difference between those simulators. It reduces the variance between those simulators. It's like if I wanted to test out a orthopedic shoe versus a normal shoe. I could have a population of people wear just the orthopedic and a population wear just the normal. Or I could do a crazy experiment where I could have one population wear an orthopedic shoe on one foot and a normal shoe on the other foot. And the advantage of that last one is I don't have to worry about, I might accidentally give the orthopedic population a set of people who are all athletes and the normal population a set of people who are all sedentary, just by accident. It might just happen that way. And so differences between the 2 populations may have nothing to do with the shoes. They may have to do with the populations. So in order for me to deal with that, I could say, well, what if every person wears both shoes? Maybe I randomize which foot they get. And that's what we did here with the batch schedules, is I was saying I could have given a different batch schedule for greedy as nearly full, but then we wouldn't know how much of this result was due to the different schedules as the policies. That's why we gave the same policy, the same schedule to both policies, and then did 10 schedules. Does that make sense? This basic idea of how we created statistical blocks. This is something that we're going to learn to do throughout the semester. Okay. All right, so what do we do? So how do we do the right stats on this now that we've done these statistical blocks? Well, here's one way that I can visualize the pairs. So I can plot all of my greedy data and all of my nearly full data together, and I can draw a line connecting these points that are paired together. So each line corresponds to a different schedule, whether your ID ended in 0, your ID ended in 1, etc. So this might be the ASU ID 0, this is the 1, this is the 2, this is the 3, and so on. Now, what do you notice about this now that I put it here? What's the consistency in these lines? Anybody? The greedy is better, or to put it another way, the lines are all sloped up to the right. So for every pairing, some pairings are much better, some pairings are not as much, but all of them have a positive slope. So for all of them, every single schedule, the greedy is better. It has a faster average time in system. So this is what I mean about variance reduction, is that if I just look at the slopes, then there's like no ambiguity. Before, when I looked at this thing, this red one and this blue one, I couldn't tell. Well, maybe, sometimes it's this way, but it's never this way. So by pairing things together, I've reduced my variance, and I can see that if I do stats on the slopes, this is an overwhelming statistical result that these slopes are positive. So that's what we're going to do. So here's another way that I can plot that. And so I've put your ASU IDs on the x-axis. I've put the greedy is the blue circles, the nearly full is the red circles. And like you can see here, the red circles are always on top. I can take the difference between each one of these, and I can compare that difference to 0. And that's what you do in a paired t-test. And so over here, I've plotted all of those differences. So this is greedy minus nearly full. And look, all of the differences are less than 0. So if I use a paired difference t-test, which is just a t-test testing with a null hypothesis of 0, then I'm going to see that overwhelmingly speaking, statistically, it's clear that I can infer that these differences, greedy minus nearly full, will always be negatives. So I have a, whatever, a 5% chance of being wrong, maybe lower than that, based on this p-value, but this is at least telling me that now I feel much stronger about my result. So there are questions about this general idea of how I've used pairing to turn 2 columns of data into 1 column of data. I was able to match up the rows of those columns of data, subtract, and then look at the differences. And then I can run those differences on a simple 1 sample t-test compared to 0. And that's what a paired difference t-test does. It's exactly that behind the scenes. And that's what we do with common random numbers. So any questions about that? Is that pretty clear? It's an example of what we could do if we pulled all of your data together from lab 2. Okay, now I had you calculate multiple things. So there's the average time in system, there's the average oven utilization, there's the maximum queue length. And I could do paired difference t-tests on all 3 of these things. Now, the question is, what output should I use? Some of these, like average time in system, show a clear difference between the 2 policies. Other ones of these, like average oven utilization, the p-value is not less than 0.05, and the numbers are all clustered around 0. So here, I see no difference, and likewise down here, no difference. So based on these 2 output measures, the 2 policies look identical. Based on this output measure, the policies look different. So before I said if I look just at this one, I have maybe a 5% chance of accidentally, making the inference that one policy is better than another. But now that I look at these other things, then I say, wow, maybe I am just in the universe where I'm in that 5%. Maybe this actually wasn't a real result. And if I just use 5% as my threshold, as my p-value threshold, then I might be guilty of phishing. So, phishing is this idea where you can say, I've got these people ate Skittles and these people ate M&Ms. I want to show that Skittles and M&Ms have different physiological responses. So I say, okay, well, did this group get cancer more often than this group? No. Okay. Did this group get headaches more often than this group? No. No. And you can keep going down through that. Eventually, you'd find something where you'd say, oh, this group got sore feet more than this group. Well, I'm going to conclude then that Skittles give people sore feet more than M&Ms do. But that's just because you were phishing. So what we're going to learn is that if you need to start sampling from multiple things, you generate what's called the multiple comparisons problem. And you're going to have to update your alpha value, your critical threshold, based on the number of things you draw. So if I have 100 different output measures, I actually have to divide my alpha, which is 0.05, by 100. So the threshold I need for each one of these becomes tighter and tighter and tighter. And that helps prevent me from getting into the phishing problem. And there are other tools we can use for that, like the multivariate ANOVA and so on. So we'll learn about Bonferroni correction. That's what I just talked about. But this is a general problem. Whenever you're going to look at these sim data, you're going to see lots of different outputs. And you can't just pick output after output after output until you get one that has a p value less than 0.05. Every time you choose to use more outputs, you have to change that 0.05 to make it lower and lower and lower, or else you'll be guilty of phishing. Does that make sense? That general idea. Things that we can kind of play with here in this lab. And again, this is something we're going to talk about in a lot more detail after the midterm. So the bottom half of the class, we get more statistical speaking, but it's something I want you to be thinking about as we start seeing variation being generated out of these sets. All right, so the other thing that I want to point out from this, this lab is even if we conclude that there is a difference between greedy and nearly full, they come back to that question, is it practically different? Will our stakeholder actually care? Because if I sample enough, I'm going to find a difference between things. So for example, I can have, I know that the orbit of Pluto has some tiny effect on my mood. If you put a mood ring on me or something like that, you could, if you sampled it for long enough and at high enough resolution, detect Pluto in my mood. Now, in a universe without Pluto, the difference between my mood as it is now and my mood in that universe without Pluto is probably so insignificant that it wouldn't affect the running of the rest of my day regardless. And so even though with enough data, you can detect a difference, if that difference is practical and useful, sometimes when you see p-values that are extremely low and sample sizes are extremely high, you need to become really, really suspicious, because you can always get low p-values by taking more samples. Because taking more samples makes you more sensitive, and eventually you're going to detect a difference, because there's always a difference. There has to be. But is that difference practical? And so this analysis, this just, is it one or the other, sometimes isn't the best way for us to assess whether things are practically different. And so one of the things we could have done is said, well, for our oven baking simulation, rather than thinking of greedy and nearly full, I could have actually simulated a wide range of oven thresholds. So 1 muffin's waiting, put it in the oven, or start the batch. 15, start the batch. 30 are waiting, start the batch. And I could have looked at these 3 measures at each one of these different levels for this smoother oven threshold variable. So now I'm not comparing 2 things. I'm saying, what is the effect of the oven threshold? And that's where things like your linear models come into play. And so I can fit a regression line to these things, and the slope of the regression line helps me say the effect of oven threshold on time and system is this much. So as you increase the oven threshold by 10, you're going to increase the time and system by this amount. And that is much more meaningful to a stakeholder, because that really tells them, in order for me to actually hit an appreciable difference in my time and system, it would mean that this operational variable might have to change a huge amount or a little amount. So that's part of the reason why we try to shift ourselves as you get kind of out of undergrad into linear modeling, and it's not just sort of this, yes or no kind of hypothesis testing. The other nice thing about linear modeling is it helps us figure out interactions between things. So I have this relationship between oven threshold and time and system, but if I change my service time to 7, so I update the service time, I might get a totally different relationship. And if I increase my service time to 14, an even more stronger relationship, where there's this weird bimodality coming up. And so linear models not only help us characterize the relationship of one thing on another, but the coupled relationship, the cross relationship, the interaction effects between oven threshold and service time. So this would tell us, we have ways of looking at this and saying there is an interaction between oven threshold and service time that you have to keep in mind whenever you're assessing your performance variables. All of that's not clear unless I do this more sophisticated linear modeling. So that's where regression lines meet hypothesis testing, is that they're kind of the regression lines, sort of the more sophisticated way of looking at the system. All right, so those are kind of the takeaways I wanted you to get from lab 2. Are there questions about this? And it's also kind of a preview of where we're going in terms of our modeling methodology that we'll use with the variable simulation systems that we're going to be working with all semester. But of course, all the comments I just made can apply to any empirical systems you're working with. If you're working in a manufacturing system, in an airport, whatever, a hospital. So any questions about that? Is it pretty clear? Or at least kind of see where I'm pointing here? It's really just kind of meant to direct your attention to the right horizon. Okay. All right, so in that case, let's end here. And so I'll do this last attendance question. And I'll put the URL in the chat for those following at home. And so the question I have here is, what is the special type of t-test you need to use when you have 2 groups whose inputs are coupled together? So when you have outputs from 2 groups, but each output is actually coupled together across the groups, what's the special type of t-test? So what's the special type of t-test used when outputs from 2 groups are coupled together? And that's all I've got for you today. So I'm happy to take any other questions. Otherwise, you have any other last minute questions about the homework, feel free to post them on the discussion board, send a note. That'd be fine too. Homework due tonight. There's a grace period until kind of tomorrow morning around 10 a.m. Lab 3, you'll get, it's already available, but formally tomorrow. Yep.
So for the bonus, to use the table 211 that uses these activity times instead. Does these refer like the ones on like the homework PDF?
The homework PDF, that's right. Okay. So use the service times and the interarrival times from the homework, but the layout from that table. And for those online who didn't hear that, the question was, just to clarify that in the bonus question, I say to use table 211 from the text, but use the activity times from the assignment. And I'm saying take the table that they present in table 211 in the text, but erase all of the interarrival times and the service times and replace them with the ones that I've given you on the top of the assignment. Any other questions? I'm looking online too. Okay. In that case, I'm ending the meeting here. Just one sec. Oh, no problem.